Whatever you know about black holes might be wrong. Even the theories of the brilliant scientist Albert Einstein may not hold up. A genius mathematician from New Zealand, Dr. Royker, who first described black holes mathematically in 1963, has now proven that the singularity of a black hole, the point where its entire mass and gravity are thought to be concentrated, does not actually exist. Let's explore this further. To understand this, we need to revisit Einstein's general theory of relativity. This theory gave rise to concepts like black holes, singularities, wormholes, and dark matter. Traditionally, we visualize gravity as a result of an object placed in space-time, causing it to curve due to the object's mass. However, this visualization is flawed because it essentially uses gravity to explain gravity, making it an inaccurate representation of space-time curvature. In reality, gravity exists because of curvature. Curvature is not created by gravity. Imagine a bucket filled with water. When you place a ball inside, the ball displaces the water, pushing it to the sides, and gravity works in a similar way. The same principle applies to space-time. If you place a ball in space-time, it displaces the surrounding space-time, creating a curvature. Scientists suggest that this curvature is what we perceive as the gravity of that object. Objects with significant gravity cause other objects around them to follow curved paths, which eventually draw them toward the center of the massive object. But how do objects get attracted? According to the general theory of relativity, everything, whether it's you, me, or a ball, is in a state of freefall, moving in a straight line. However, when a massive object bends space-time, straight freefall becomes curved freefall. Because of the curvature of the path, the direction of our motion shifts towards the center of mass, creating a field-like attraction, which we call gravity. Now, why did I explain all this? It's because the event horizon of a black hole, its boundary, ties everything together. A black hole is called such because even light cannot escape its pull. This phenomenon is possible only if we assume that the flow of space-time across the event horizon exceeds the speed of light, including the transfer of information. When an object, even light, enters a black hole, it cannot escape due to the light-speed barrier. This creates a paradox. Can anything in the universe travel faster than light? According to the general theory of relativity, the answer is no. This paradox highlights a critical flaw within the theory itself. The very assumption on which general relativity is based breaks down inside a black hole, leading to strange and unexpected results. Scientists refer to this breakdown as the singularity. However, not all scientists agreed with this concept. One physicist saw it as a major flaw, arguing that the singularity assumption, that all black holes are stationary, is incorrect. Black holes form when massive stars collapse, and according to the law of conservation of momentum, any rotating body will continue to rotate unless acted upon by an external force or collision. Therefore, black holes should also rotate. This realization led Dr. Royker to question the existence of singularities altogether. We've been told that a singularity forms when a black hole is stationary, with only its event horizon rotating. This causes everything that crosses the event horizon to fall towards a single point, leading to infinite gravitational pressure, what scientists call a singularity. This explanation makes it clear how singularities are thought to form within stationary black holes. However, as we've learned, black holes are not stationary. They rotate. This means that a point singularity cannot exist. In a rotating black hole, objects that cross the event horizon spiral inward, rotating around the center rather than falling directly into a single point. Their motion resembles that of motorcycles riding the well of death, where, due to the high speed, bikes spiral downward rather than falling straight. Similarly, in a rotating black hole, objects don't fall directly onto a central point, but instead orbit around in a ring-like motion indefinitely. As a result, the mass of the black hole is not concentrated at a single point, but along this rotating ring. In essence, the singularity is not a point, but rather a ring-shaped motion, confirming that black holes rotate. This simple fact challenges Einstein's theory. But does this mean that all the discoveries made using general relativity are now useless? Not at all. Our GPS system relies on the time dilation principle of general relativity due to gravitational potential differences. GPS satellites orbit about 20,000 kilometers above Earth's surface, where gravity is weaker compared to the Earth's surface. As a result, the clocks on these satellites run faster than those on Earth. To correct this, the speeds of the satellite clocks are adjusted using relativity calculations to match Earth's time precisely. Without these corrections, we would experience inaccurate data, like receiving morning traffic updates in the evening. But this doesn't happen. GPS is often accurate to the minute, demonstrating the ongoing validity of general relativity in practical applications. However, Einstein's theory struggles to predict certain things, like what lies inside a singularity or what occurred before the Big Bang. This is where it falls short. The concept of the ring singularity might not completely replace general relativity, but could serve as an addition or upgrade to the existing theory. So far, we've relied on Newton's laws of gravity for rocket launches and Einstein's general theory of relativity. But when it comes to understanding what happens inside black holes, Roy Kerr's theory fills the gap left by Einstein. The next frontier in our understanding of gravity is quantum gravity and its true nature. We still don't know what exactly lies inside a singularity, as the particles there start to exhibit quantum effects. To fully grasp singularities, we need a theory that can explain gravity at the quantum level. However, one of the most fundamental challenges facing the scientific community is merging these two major theories, quantum mechanics and gravity. So why can't quantum mechanics explain gravity? There are multiple reasons, and we'll dive into them in the next video if we hit 50K likes and 10K comments. See you in the next video.